Now let's look at the Jupyter Notebook for the experiment example. Here is our outline for the experiment. The first step is to import the dataset and understand the data. Then we will pre-process the data by removing the missing values and normalize some variables. Next, we will split the dataset into training set and testing set. And after that, we will focus on training set to deal with the class imbalance issue. And after that, we can train and test the classifiers. I also include the exploratory data analysis here to give you some example how we can understand the dataset. So let's begin. First of all, we should import some helpful libraries. Note that if the package you want to import haven't been installed, you need to install it either in the Anaconda Navigator or in the Jupyter Notebook using the code pip install. For example, if we want to install the NumPy library, we need to use pip install NumPy. And if you have already installed all the libraries, we can directly import the NumPy for linear algebra, Pandas for data preprocessing, and matplotlib for plotting. Next, we can load the dataset with the help of Panda. Here, I use this head function to display the first 5 rows of the data frame. You can see the data frame consists of 31 columns, including 30 predictors and 1 class. We can use this describe function to get the statistic descriptions of the variables. According to the output, we can see that the variables V1 to V28 are scaled before the PCA transformation, so they are of quite similar scale and don't need to be normalized again. However, for the feature, time, and amount, they are on a greater scale than the other 28 variables, and thus should be scaled. Nevertheless, it would have greater influence on any other features on the model. We can use this info function to check the missing values and the data type of each column. It shows that there is no missing value for any of the variables, so we don't deal with the missing value. We can also use the value counts to check the target classes. As we can see, the classes are heavily skewed. We need to solve this issue later. If we use imbalanced dataset for our predictive models, our algorithms will likely to overfit, since it will assume that most transactions are non-fraud and performs badly in detecting frauds when it was applied to new dataset. The next step is to preprocess. Since we don't have missing value, here we only need to normalize the time and amount column. I use one package called Preprocessing from sklearn and use a function called standard scaler to transform amount and time into scaled version. We can also check the data frame using the head to display the first several rows and see if the transformation is succeed. Next, we should split the dataset into training set and testing set. We will use a function from sklearn2 to split the training set and test set. The first step is to separate the class with the variables, and then we can use this function and specify certain test size ratio, for example 0.3, and then we can split the data into training set and testing set. Here I add the original in the name of the variables in order to distinguish them with the balanced X-train, Y-train, X-test, Y-test. We can check their data type and also see if both the training and testing set has similar label distribution. And we find they are quite similar. Now that we have the training set and testing set, we can focus on training set and handle the class imbalance. There are many techniques for this. However, I will only use the simplest one to give you an intuitive. The random undersampling technique basically removes data to have a more balanced dataset and thus avoid our models to overfit. To conduct random undersampling, the first step is to determine how imbalanced is our class. Here, we can output the classes in the original Y-train, and we find there are only 356 fraud observations. With this knowledge, we can randomly undersample the non-fraud variables, non-fraud observations, to the same amount as the fraudulent transactions. To do that, I first obtain the original data frame by combining the original X-train and original Y-train. Then I will shuffle the data frame and get the first 356 rows of the data frame. So that is stored in the variable non-fraud train. I also get the fraud train, which contains all the fraudulent observations in the original Y-train dataset, and concatenate the fraud train and non-fraud train to get the balanced training set. If we check the class in the balanced training set, we find there are the same amount of fraud and non-fraud data. However, this random undersampling technique has some disadvantages. There is a risk that our model may perform not as good as we expect because there is a great deal of information loss because we bring the around 200,000 non-fraudulent observations down to 356. Now that we have our data frame balanced, we can go further with the analysis. But before we conduct the experiment, the machine learning, build the machine learning model, let's do the EDA. One of the most useful EDA technique is the correlation heat map. Many of the times, the machine learning algorithms are sensitive to the correlation between features. If many of the features are highly correlated, the algorithm will, with all the features, may have lower accuracy. So in that case, we may need to do feature selection. Although in our case, we have a great number of observations, but not many variables, so it's not very important or necessary for us to conduct feature selection, but it's still worth doing the EDA to see the correlation. You can use the core function and use the Seaborn library to plot the heat map for the variables correlation. Here, I plot not only the correlation map for the balanced sample, but also plot it for the imbalanced sample. Because if we compare these two, we can find if we don't deal with the class imbalance in the dataset, then the correlation can also be biased. So next, we should focus on the balanced datasets sample correlation matrix. If we look at the last column or last row, it is a class, and we can find its correlation with different predictors. For example, the class is quite positively correlated with V10, V12, V14. Oh, sorry, negatively, but it's positively correlated with V4, V11, and kind of with the V19. This suggests that these variables might be predictive for the class. However, some of the variables are highly correlated with each other, so they might also bring down the accuracy for the model. We can further explore the features distribution using the box plots. The box plots show the difference between the two classes in terms of each variables clearly. In this case, we can tell the V14 is quite predictive for the class because the two classes are quite separate, have very different values in terms of V14. Now, we already obtained a good understanding of the dataset. We also have the training set and testing set, and also dealt with the class imbalance in the training set. Now, we can use different predictive models to see how accurate they can make prediction or detection. So here, I first separate the X and Y for the balanced training set and keep them as series. Next, I import 4 kinds of classifier libraries, including Logistic Regression, SVM, KNN, and Decision tree, which are all introduced before. And I store the name of the classifiers and the classifiers into a dictionary. Then we can use a loop to feed each of the classifier and make prediction and also evaluate the model's performance for them. So we can see for logistic regression, the accuracy score is quite high. It's around 0.97. However, for the F1 score and RCUC score, they are quite low. Normally, we expect RCUC to be above 0.7 or 0.8 to be reasonable. However, here it's almost like a random guess. This is called the confusion matrix. It shows the predicted label versus the true label. So this area means the true positives, meaning that the model make the correct prediction for the true label. However, this area shows the false negative, meaning that although the true label is fraud, the predicted outcome is non-fraud. These false negatives are quite high, so the prediction performance is not good. It's similar for KNN and support vector machine, although its RCUC is better, and decision tree. However, here we are only using the default hyperparameters for each of the classifiers. We can also try to tune the hyperparameters to see if the performance get improved. To do that, we can use the grid search CV, which can make different combinations of the parameters for each classifier and output the best estimator for them. We can print the best models for each of the classifier. and see the best combinations of hyperparameters. And if we use them to train and evaluate the model, we can see the logistic regression has a higher RCUC. This 0.79 is reasonable, and the F1 score is also high. For KNN, the RCUC score improved a little bit. For support vector machine, also improved a little bit. And it's the same for decision tree classifier. So we can tell the logistic regression in this setting performs the best among the other several classifiers. And we can also see that when we have imbalanced dataset, the accuracy score is not good because it can be skewed by the imbalance. However, the F1 score and RCUC score are actually more comprehensive because they, by nature, take into account of the different classes. So in this case, we may be better to use F-score and RCUC score for the model evaluation.